going to start recording. That way, in case anyone else wants to have homework questions repeated. Kelly has a question. Go for it.
Yes. So mine is on section 2.
All
I'm
right.
getting stuck on 26.
Okay. I have
I think it's just a lot at once, so I'm getting like, yeah. Yeah. So I don't know exactly. I got 25.
Okay,
And then ones
26.
before that. Yeah.
26. Okay, so this is where we're starting to calculate pieces of the R, R
Yes.
core, V, etc.
Hmm.
So, all right.
Maybe just a review of switching back and forth from R core to R. I thought I understood, but then when I got to 26, I was wrong. So maybe I don't understand.
Sure. So I can point you to where these things are. So, for instance, 25, if we start with that. So, given an
Mhm,
AR1 R only model. So, that's your cue as to where to look.
mhm.
And that is in lecture 4. If we get to the R only models, the AR1 model is given on slide 12. Okay, can you see that with me?
Yes.
Okay, then the information that is given in the question is the autocorrelation value, that's the AR1 number, and then
Mhm.
the residual, which is what SAS calls the total variance. So the residual comes pre-squared, so to speak. It's given in the variance form. So that number that's given in the question, so for instance, if I pull up my version of this, my version has a residual variance of 16.4 and an AR correlation of 0.5. If I were to calculate row 2, column 1, like where my mouse is right now, for instance, it would be
Mhm.
that R value that's given in the question multiplied by the residual variance that's given in the question if I were trying to calculate something in the R matrix. So R is the variance covariance version. So the off diagonal elements right here is how the model gives you predicted covariances. To translate this R matrix into an R core, which is the correlation version, just swap out these variances for ones. Because in a correlation matrix, all the variances become ones. And so then the only term that contributes in R core is just the R value. And so then you'll have to look at what the question is asking in terms of where in the matrix, which element. In this question for 25, for instance, it's element 3, 1 in R core. So I would go down to row 3, column 1, which is right there.
Mhm.
And so then that is the predicted correlation given by the model would be the R value that is in the question squared. If I had asked for R core for 4, 1, it would be the
Be
R
cubed.
value cubed. Exactly.
Okay. Okay. I think I got it.
Yeah.
I think
So,
it's just a lot of like, I don't want to say adjectives because it's not adjectives, but like AR1 R only model and then all the parameters. And I'm like, oh my gosh.
yes, it's word salad overload.
Yeah.
But that is actually the point of the homework is to start getting you used to seeing these things and immediately thinking, okay, what is that? Because there is a lot of new terminology that goes along with these models, for better or worse. So we will continue using the terminology and practicing with it and adding to it throughout the semester. So for those of you who are also feeling like this is a lot, yes, the answer is yes, it is. But it's okay if it doesn't all make crystal clear sense right now. That's okay with me. This is just your first pass at starting to get acquainted with this terminology. Okay, did that answer your question, Kelly?
I think so. I'm gonna have to rewatch. So I'm glad you started recording
Okay.
so I can like slow it down and think about it. Um, Yes, that should answer it.
Okay, so like for 25 and 26, for instance, those are asking about elements in the R core version and then the R version of an
Hmm.
AR1 model. So that's all on that slide. The last four questions in this section are asking about the random intercept plus autoregressive correlation model. That one is in slide 21, where the homogeneous version is at the top. And so R is the variance covariance version here. And so in this case, the residual variance that's given would go to 1 if I'm asking about R core. And then V over here is the total, the marginal put back together again. That's variance and covariance. And if it's the correlation version of V, then all the variances go to 1 as plus this intercept variance correlation. So there's a little bit more math in that one, I think, but I don't think I asked about anything that was going to be too bad, relatively speaking. It could be worse, let's put it that way.
Okay.
Even though it may not seem like it. And okay, so the other questions I can remind folks, these questions up here about which of the following will have a valid likelihood ratio test statistic. How to approach this question is to first ask yourself, are the two models to be compared in the right order? The right order is the model that has fewer parameters has to go first, followed by the model that has more. That is the only way that the net result of the subtraction will be a positive number. So some of these options are wrong because they're in the wrong order. The other thing to ask yourself is, are we talking about ML or are we talking about REML? The models to be compared under ML can differ in either their mean side or their variance side or both. So basically any kind of nested model comparison is acceptable in ML. If you're in REML, then the models to be compared can only differ in their variance side. So some of these options break that latter rule of using REML but then having two different means models. The reason for that we will get into more detail later, but it boils down to the fact that REML is operating on the model residuals, and if you have different predictors in the model, then those residuals are defined differently and they're on different scales, and so then it's like apples to oranges in terms of what's being maximized. So in REML, model comparisons for the variance side only. Okay, who else wants to ask a question? Homework 1 is what we're talking about for those of you just joining us. Nobody? Am I going to have lots of people in office hours then? Yes. Okay, that's cool. So the way we do office hours, for those of you who haven't joined us yet, you're welcome to come and hang out. Office hours are for everyone because there's 30 of you in this class and I've got 9 people in my other class, so that I can help as many of you as quickly as possible. Everybody can come hang out. You can sit in the background and do your work, or you can come and ask questions. Put your name in the chat window when you have a question. I'll get to you, answer your question. You can go back working and I'll roll through as many questions as possible. So everyone is welcome to join. You don't need an appointment. You just have to be willing to share time with your classmates. But odds are good, since you're all working on the same thing, that there will be overlap in the questions and answers provided. So, okay. So really, we're good for right now with homework?
Yeah, I have a question on the last lecture.
Okay.
And I think it's just clarification. So when we were talking about like those tapered pants that just get tapered too much, like diminishing too quickly,
Yes.
I guess I kind of got bogged down on how we solve, like, quote unquote, solve that when we take out the random intercept. So can we just talk about that?
Yeah. So that's it. This combination is a good example. So the random intercept plus AR1 model versus the AR1 model. Let me go back to that slide. So I was going to go through, I think, the end of this lecture anyway, but we can touch on this particular example because it's useful in illustrating the point. So I'm on slide 12 of lecture 4. This is the AR1 R only model. This is one that I have never seen fit real data. I'll just be honest with you. It's in every stats textbook that focuses on longitudinal models, and so I present it because I want you to have seen it, but it doesn't fit. And the analogy that I use to describe why it doesn't fit is tapered pants. The problem with tapered pants, why they look bad on people, is that they narrow too much relative to the waist. And the problem with this correlation matrix prediction is that by taking a correlation and squaring it and cubing it and fourthing it and so on, it makes the correlation die off at the later occasions. So it might predict that there is no more correlation if you get far enough out in terms of the lags, how many occasions apart they are. So if I say lag 1, that means adjacent occasions, 1 unit apart. Lag 2 is 2 units apart. And so thirding it, fourthing it, fifthing it, sixthing it, in terms of the powers of the R, it makes it die off. But in longitudinal data, a lot of times there's just a constant correlation regardless of how far apart the occasions are, because people tend to be consistent. If you have person mean differences in a variable, if some people are just, worse off all the time or better off all the time, that induces a positive correlation that stays across the board. So the AR1 doesn't fit that. It predicts the correlation is going to decay a lot more than it actually does in a lot of data sets. So the solution to that then is to break apart the problem. So the idea of these R-only models versus G and R models is divide and conquer. R-only models like this one right here, like the compound symmetry ones and the Topolitz ones, they try to predict all of the correlations in the data in one matrix. And because there's a lot of covariance from occasions from the same person, these structures have to be fairly complex to be able to get all of that in there. The logic of the G and R models, as I call them, welcome to the jungle. We got fun and games. The G and R models, and I wait for it, a few of you smiled. These break apart the problem. So rather than trying to model all of the correlations in one place, we say, okay, how about we take the part that's common across persons and put it over here. So we're going to take the model random intercept variance and set it aside in a level 2 G matrix. Then we're just going to look at what is the pattern of correlation of the within person residuals specifically. Those tend to have much less correlation, and it does die off a lot more quickly because it's sort of like the correlation is coming from two places. So that's why this, let's see, find here. This one, slide 21, jumping ahead here. This is saying that there are two reasons for the observed complete pattern of correlation. So what ends up in V here is a function of two things. So these off-diagonal elements here that describe the relationship. Part of the reason why the occasions are related is because they come from the same person. That's the random intercept variance part that's creating a constant correlation. Beyond that, occasions that are closer together in time are more related also. So it's a divide and conquer. There's two sources of correlation being put in here. And this pattern works pretty well for most within-person fluctuation type of data. It's only 3 parameters, no matter how many occasions you have. And this is the one approach that can be extended to unbalanced time. So within R and within SAS, I haven't found it in Stata, but it may be in there somewhere that I'm not privy to. You can have unbalanced time occasions, different intervals between persons and different occasions observed between persons, and still fit a structure where this pattern is being predicted. So that's why I had put a flag on this one as one of my faves.
Okay, can I kind of repeat the way that I understood that?
Sure.
So we're saying that the within person residuals do die off quickly like AR1.
Mm-hmm. Their
So
correlation
then,
does, yes.
yeah, in my mind, that translates to it's okay to wear tapered pants by myself in my home because it's just within me. That's the way I can remember it.
Yeah, I think that works. These sort of combined structures, like I think of as like just going to a tailor. Like you make sure that everything fits, but then you can customize it. Like it's divide and conquer. You don't have to buy it off the rack. The hour-only models are like off-the-rack pants where you got to try and make everything fit, and it's really hard to do that. So if you're willing to break it into pieces, and fit the largest or most difficult part of your body, and then you can take it to the tailor.
Mhm.
That's the idea that I map onto this. But if you want to think about tapered pants in your living room where no one's there to judge you, that works too.
Okay.
Whatever speaks to you.
Okay, that answers my question.
Okay. So other questions about specific things? Otherwise, we can do a little more general review, looking at the end slides we didn't get to.
I have a separate question. I'm just
Okay.
full of questions today. So it's another one about how adding in random intercept solves, or doesn't solve things, but separates things.
Mm-hmm.
So I have on my notes that adding a random intercept means that you can choose which topolets to include.
Mm-hmm.
Can we just talk about that? And then that's my last question.
Yeah. So for instance, this is slide 23. This is another combination model. This is a random intercept plus a tope 2 R matrix. So what is in R then? 2 refers to the diagonal of residual variances. So you have that no matter what. And then the second parameter is the covariance between adjacent occasions on the first off diagonal. So 2 parameters in the R matrix is why it's called tope 2. So this model says that occasions that are 1 unit apart have their residuals correlated only. So it's different than Ar1 because Ar1 does predict a correlation through all the residuals, it's just that it dies off. This one shuts off. So it's 0 for occasions that are more than 1 unit in time apart. If that's unrealistic, you could do a tope 3. And so then you would have a covariance that is for adjacent occasions, a covariance for occasions that are 2 apart, and a residual variance. So that's where the 3 comes from. So that's a savings relative to the full order topolets, I mean.
Okay, so if we didn't have a random intercept, we would have to estimate all the topolets?
Yes, all the bands.
Now I get it now. Okay, that makes sense.
Yeah, because otherwise you'd be saying that, occasions past 2 apart or 3 apart are completely unrelated, and that's not true. It's that they're not additionally related after you control for the intercept.
So the ones that we don't specify after 2 just take on the random intercept?
That's right.
Okay.
That's exactly right. Yep.
This is coming from the homework, but could you have a random intercept that is 0 and then the R matrix diagonals would equal the V matrix diagonals?
Yes, that is theoretically possible, but very unlikely.
Okay. And I guess I'm asking that because of the homework. So does that mean that the homework is based on like practically possible options?
The key idea is that V is these 2 things put together. So
okay, got it.
Whatever's in V should be more because they're combined.
Yep. Okay. Okay, thanks.
Yeah. Put together or marginally, I think, is total. All of those ideas are what make sense. But yes, that's what I was sort of going for, is just vocabulary. G is the level 2 things that vary across people, like the intercept here. R is within person residuals, and you put them together and you get the marginal prediction of all the correlations across time. That's V. Okay. Others? Thank you for the questions. I appreciate that. All right, let me make sure I'm recording. I'm always paranoid that I forget to hit record, but I've got it. Okay, so then, yes, backing up just to hit sort of the big picture, because it's very easy to get lost in the details of this and the terminology. The big picture is that we are trying to, let me get the slideshow going here. This is slide 19. What we are trying to do is for data that show within person fluctuation specifically. So this is a set of models designed for ecological momentary assessment kinds of data, things where your phone pings you so often and you answer questions, observational studies where you're collecting data from the same person but you're not trying to fix them, and you're not expecting any sort of systematic development or change. So just like an observational data from the same person, and seeing how people vary around their own means over time. That's the kind of data that these models are designed for. And even though time isn't a factor that we really have to think about in terms of change over time, we do still want to make sure that if there are different variances across time and if there are different patterns of covariance across time, that whatever model for the variance that we specify matches those patterns in the data. So these are just choices for different patterns that are available. There's literally like 36 of them in SAS. Like I only showed you like 4. There's way more than this. I know, right? They're for spatial data because like if you collect data from people like census data, data from people who live closer together are more related. So you could have like a 2-dimensional correlation thing over time and over space, like weather data, for instance, that kind of stuff. So correlation structures more generally, there's lots and lots of choices. But the object is just to try and find a pattern that matches what's in the data and try to do it as parsimoniously as possible. And what I am recommending as a general strategy is to estimate a random intercept first, because we know that that predicts a constant common correlation across time because some people are just higher or lower than others, period, mean differences. Then it's going to be easier to find a pattern that works for the data if you're only trying to pattern the residuals that are left. So the residuals are like the little lines around the person mean, like the difference between your E and your mean. That's what we're trying to pattern. So they have a lot less variance, they'll have a lot less covariance, and any covariance that they do have is less likely to occur at further distances apart. So you can get away with a simpler model if you break it into pieces in terms of what's predicting the correlation. And so then we just did some kinds. And this, in case you're curious about how all these things relate to each other, is a figure from my book. This thing took me like 8 hours to build, so I have to make sure to point it out to you because this was like a whole day of my life thinking about how to present this. This describes how things are either equal to each other or nested in relative to each other in terms of either R-only models or the combined models that are either homogeneous across time and variables that are or models that are heterogeneous across time. So for instance, if you have R-only compound symmetry, this box right here, that's where we started. That was the very first longitudinal model that we had. That is within person repeated measures ANOVA. That's what it is. That is the same thing as saying that you have a random intercept in G and you have a diagonal R matrix. So the R matrix for the residuals that are left says there is no more correlation. It's all taken care of because of G. Those are the same thing. On the heterogeneous side, you have fewer equivalencies. You do get into, like for the unstructured versions, the 2 versions I showed you of that are equivalent. So there's more than one way to kind of approach these problems. Not all of these are available in all software packages. So Topolitz, for instance, I could only get the homogeneous version in Stata, I think. The heterogeneous version isn't in there. I couldn't find it in R at all. So it may depend on what's available to you. What would be the best sort of choices. So these are just choices. That's what I'm going for. Here's some catches in terms of things you can and can't do. So there's certain combinations that don't make any sense. So for instance, you can't have a random intercept in G and a compound symmetry correlation in R. So take a minute to think about that. Compound symmetry says there's a constant correlation. A random intercept says there's a constant correlation. Those are redundant. So you can't have both in the model at the same time. You can't have more parameters estimated than you have variances and covariances. So if you fit a random intercept, whatever you have in the R matrix has to at least be missing one term because you've already estimated a random intercept. And SAS will let you know if you ask for something that's impossible. It will like return a set of dots and like, nope, no thank you. Yeah, so this is stuff we talked about already. So those are the 2 families of models, R-only models, which are talked about but I think are less useful, The combination models where you split the correlation into two places, random intercept versus residuals, those I think are going to be more useful in practice. And then bringing this back to, yeah, that's just more caveats about the code. All of the choices. So if you think back to these choices as a menu, relative to what is possible in ordinary least squares, relative to what is possible in traditional repeated measures ANOVA, you have two choices. You have compound symmetry, which is the univariate approach, or you have the multivariate approach, which is unstructured. That's it. Those are your choices. There's a whole bunch of options in the middle that are possible once you switch to likelihood estimation. Not all of them make sense for a given type of data. A lot of them rely on the idea of equidistant time intervals, which doesn't fit a lot of data, but there are more choices. And so these are the choices that I would recommend when you are dealing with the context of within person fluctuation. Where we are headed in the next unit is, okay, what would it look like if it's within person change instead? Then a different set of choices is going to be more useful to you. Okay, there. Questions on any of that? Does that feel a little better? A little bit, maybe? Is it acceptable answer? I'll take it. It's an honest answer at least, right?